All right, so welcome to Math 389 Advanced Analysis. And so this was the picture we were talking about from last class. I have just, posted it over here. Pictures worth 1,000 words. When you look at this, you can see there are only 3 regions in the country that are either rooting for the Patriots or against the Rams. And there's a story behind all of it. And we talked about that last time. And the whole point is, when you're looking at data, try to find which of the places that really matter. Why New England is rooting for New England is pretty obvious. Louisiana, their team, the Saints, lost to the Rams in a horribly officiated game that was so bad, the NFL apologized afterwards and said, boy, did we screw up. And then the last one is the Rams used to be the St. Louis Rams, and then they moved to Los Angeles. And that's why this last little bit is rooting either for the Patriots or against the Rams, because they were pissed at people moving. So again, try to figure out in whatever problem you're doing, what are the key features to focus on. So what I wanted to do, so it seems like it has adjusted the size of text. This is not good. So let me just try to quickly fix this. I won't worry then about things being in the wrong color. There we go. Fine. Back to the keyboard. Okay. Always nice when things change on you. Okay, so the to-do list for today is talk about violating conditions and theorems and finding counterexamples. So this is a nice way to just transition to a new topic. This class is about operations of order. So I am dedicating this class to one of my professors from when I was an undergraduate. I will be emailing him later today and thanking him. This is Professor Peter Jones. I took 3 wonderful analysis classes with him. I've shared some of his wisdom in the past. He's the one who taught me that there are 2 things you can do in mathematics. You can add 0 and you can multiply by 1. And then he paused with me because, the log of 1 is 0. There's really only one thing you can do in mathematics. And so it's finding clever ways to do nothing. The next one that he gave me is, take a theorem, remove a condition. You should be able to find a counterexample, or typically the proof is much harder. Doesn't mean always. Sometimes when you have extra conditions, you might focus on a property that's not really essential. And you might then go to a more advanced thing that you don't really need. But as a general rule, usually the conditions are necessary. So if you violate a condition, usually there should be a counterexample. And then the last is consider a claim. If it seems like a standard claim and it's something you should have heard of and you haven't heard of it, then it's probably false. This works better the more math you know. When you don't know much mathematics, it's not really that helpful. But as you get old, and I will talk about, it saved me on my old exam at Princeton, the algebra section, when they asked me a question. And I'll talk about this later when we get to that. It goes, I've never heard of this. And boy, I remember reading a lot of algebra books preparing for my oral exam. If that was a true theorem, I'm sure I would have read of it. I haven't read of it, therefore I'm going to guess that it's false. And this is correct, now prove that it's false. But it gave me the right way to look at things. All right. So the first is real analysis is a prereq for this class, correct?
I think so.
I think so. Okay. So I've just pasted for completeness a slide from Wikipedia on what is supremum, what is infimum. Hopefully everyone has seen this before. Have you seen supremums? Beautiful. This is just for completeness. And then definitions of lower bounds, upper bounds. Again, everybody should have seen this for completeness. The slides are just there. And then we have lim sup and lim inf. Right? These are the fun ones. So the lim sup is you look at the supremum of all of the terms in your sequence from some point n and onward. And for fixed n, you look at what's the supremum. And then you do that for each n, and you take the infimum of all that. So what this means is, for the lim sup, I can change finitely many terms of the sequence, and it's not going to affect anything. So the lim sup is stable under removing finitely many terms. What about the supremum? Is that stable under removing finitely many terms? No, you could remove the largest term, and now the supremum has changed. So lim sup and sup are very different. So it's probably not a bad idea to do some examples and just calculate, what is the lim sup limit. So for example, maybe I let an equals 1 minus 1 over n if n is even, and 1 plus 1 over n if n is odd. So does the series converge? So
Series or sequence?
Sequence, right? So the limit is n goes to infinity of an equals 1. So if it equals 1, what's the lim sup? What's the lim inf?
1.
1. So if the limit exists, then the lim sup and the lim inf equal the limit. But the lim sup and the lim inf can exist without the sequence converging. What if I let an equal -1 plus -1 over n? Does the limit exist? Oh, sorry, -1 to the n. Sorry, -1 to the n plus -1 to the n over n. So now the limit as n goes to infinity of an does not exist. What is the lim sup as n goes to infinity of an? 1. And lim inf is -1. What is the supremum of an? So 2. Why 2? So what's the infimum of an? The infimum is -2. And what is the supremum? I think you would take n equals 2,
3 over 2.
and you would get 1 plus 1/2, so you'd get 3/2. I think you can start playing some, more interesting games where you could have interesting things happening. Maybe I change the definition of a at powers of 2. And you can have, different types of convergence happening. Okay. So here, how many of you have seen the monotone convergence theorem? Have you seen proofs of this? Have you done this in measure theory?
We did it in real.
You proved this in real.
Yeah.
Okay. I can see that with I can see that with Leo.
That's not the same.
There's different versions of the monotone. There's the monotone convergence theorem for sequences. This is the monotone convergence theorem for integrals.
Oh no, I have seen this stuff.
Okay, have you taken measure theory or ergodic theory?
No, but over spring break, I finished reading my analysis textbook.
Okay.
It was in there.
Okay. So this is a wonderful result. So there's a bunch of gobbledygook in the beginning in terms of just where do we live. Think of it as I'm living on the real line. I'm looking at nice functions. And it says, imagine you have a sequence of functions that are pointwise non-decreasing. So your f1 less than equal to f2 less than equal to f3. And let's assume that the pointwise supremum is a measurable function, which basically just means it's nice. Then, I'm sorry, that's a consequence. Then the pointwise supremum is a measurable function, it's nice, and the supremum of the integrals is the integral of the supremum. So one of the big themes of this class is interchanging orders. When are you allowed to flip the order of two operations? If you're an economist, you don't even realize this is a question. Of course I can interchange. If it's a physicist, you realize it's a question, but you trust the mathematicians. In our department, we prove why you can do this. So what it's basically saying is, if we have a sequence of non-decreasing functions, then the supremum of the integral is the same as the integral of the supremum. So we need to violate conditions and see if it's still true. Or instead of looking at the supremum, we have to look at something else. So we either have to, one is violate maybe non-decreasing, or we could change supremum to something else, or maybe violate, non-negative. So it's possible that the result might still be true. But these are some natural things to violate. Anybody have any thoughts as to what would you like to violate first? The non-decreasing, changing supremum to something else, violating non-negative. Okay, so what would you like to?
Well, you just violate non-decreasing.
Okay, so what you want to do now, and so one of the nice things about teaching this class is I often don't have to prepare and just see what do we want to do. So we will have a sequence of functions, sequence of Fn that are not non-decreasing, show the supremum of the integral of Fk does not equal the integral of the supremum of Fk. So can you come up with any examples of functions that are not non-decreasing? That gives you a lot of flexibility now. So one thing is to try to make it so that all of the integrals are the same. If all of the integrals are the same, then taking the supremum is really doing nothing, right? But maybe they're the same because the values assigned, it's changing where they are. And so then if I look at the supremum of the FKs, maybe that becomes large. So again, to me, it's the thought process that matters. So what we want to do is we want to come up with a sequence of functions. So maybe find Fk sequence so that the integral of Fk is constant. What should that constant equal? 1. But the supremum of Fk is large, or has large integral. So I want a sequence of functions that integrate to 1.
Triangular bumps.
Okay, good. So one is we could have triangular bumps and move them around. Any thoughts onto how to do that? Your idea can be made to work. And I am the president of a society that could help. Yes. The Fibonacci's could help us. Let's let phi equal 1 plus root 5 over 2, which is the golden mean. Okay. Choose Fk to have a bump at k phi mod 1. So we're going to keep the integration in the interval 0, 1. And we'll do a wraparound. So here is 0, here's 1, And then here's 0 again, just wrapping things around. And so what we want to do is, here it maybe is k phi mod 1. And then let's choose our function. It doesn't have to be continuous. We could choose it to be some kind of rectangle of height n, or we could choose maybe a triangle with slightly larger base. And then we can set it up so that all of those integrals are going to be 1. But the integral of the supremum is clearly going to beat that because we'll have 2 separate bumps. Is this enough detail that you're convinced that we can come up with a counterexample? Do you want to write this up? So I'm reading a biography of John Conway, and I was fortunate to know him when I was a graduate student. Absolutely amazing person. But he had some results that he just didn't want to write up because the fun was proving them, but the write-up would be painful. So can we come up with a better example? So this is enough to prove that the supremum of the integral is not always the integral of the supremum. But it would be a little bit of work to write this. And so I think there's an easier way to do this. How with cosines?
You could, like you could do cosine kx, and then as k goes to this, also,
So maybe cosine squared, because it needs to be non-negative.
yeah.
So this is one possibility. Another is cosine squared kx, or maybe cosine squared k pi x, something like that. And look at that on 0, 1. And then all of those will hopefully have maybe the same integral or something nice. And since we're taking the supremum, for the triangles from part 1, eventually you'll have 2 of them that are well separated. So the integral of the supremum will be at least 2. So that's clearly enough to show you that it can't work. Part of the joy of real analysis is collecting a bag of counterexamples, a bag of good functions to look at. Whenever I teach probability, I love to focus on the Cauchy distribution because you can argue whether or not it has a mean. It does not have a finite variance. And this allows you to test and see how universal are some results. So what I want to do now is on level n, have rectangles of height n and base 1 over n from, or let's do on 0 to 1 over n, then 1 over n to 2 over n, then 2 over n to 3 over n, dot, dot, dot. So what I'm basically doing is, here's the first one, then the second, then the third, and we keep going like that. And then for the next level, we go up higher over a slightly smaller. And so each one of those boxes is going to have area under it of 1. They're all going to be non-negative. What's the supremum going to be? So for any point, what's the supremum going to be? Can't be n because n is going to infinity. Yeah, well, it's infinity. You give me any point on the interval, eventually at level n, I will have one of the functions defined on the interval containing that point. So the value I assign there will be at least n. Then at level n plus one, something will hit it, and it'll be at least n plus one. Then at level n plus two. So, really a good way to count is between powers of two, maybe, or something like that, whatever. I'm just doing n plus one, n plus, that's fine. And by looking at it like this, the supremum of the function is identically infinity. What about the previous where we used rectangles and triangles? Is the supremum also plus infinity for any point? Why not?
Like don't move them around the height.
So okay, so the height is remaining the same in what you're doing? Okay, I thought the height was n.
I'm just changing the location of the center.
Oh, you're changing the location of the center. Okay, so then if you do that, then yes, then the supremum would be bounded. So so the first one we can do with a bounded supremum. For the one I'm doing here, could I do this with a bounded supremum? So here my functions are getting larger, right?
Instead of going up into infinity to get like high to a certain ceiling to supremum to an everything.
Okay, but then are they going to be getting over smaller windows? In which case, then each integral fk is not the same. There's a really stupid trick I can do. So this is almost embarrassing, but almost is not the same as embarrassing. So Fn of x is Fn mod 10 of x. Right? Just take a sequence of functions. And so if I just do this trick by breaking it up into intervals 0 to 1/10, 1/10 to 2/10, 2/10 to 3/10, and I just cycle through them, then the supremum is going to be 1 everywhere. The integral of fk is always going to be 1/10, but the integral of the supremum is going to be 1. So again, when you're trying to prove something is true or not, step one is just come up with a solution. Then maybe you want to try to find the best solution. You want to try to find something that really illuminates what's going on. There's also what is easy to convey, what is easy to write up. A lot of times when you're proving theorems, you have to decide, do I prove this in the greatest possible generality, or do I prove it in slightly less generality, but it's going to be easier for people to read and understand? One of my favorite referee assignments, and I know this is being recorded, is I was asked to review a paper because the author cited one of my theorems. And when you're trying to find a referee, if an author is citing someone's work, that's a natural person to ask. And so the journal asked me, have I told you the story? And so I told the journal, I'm happy to referee the paper for you, but in the interest of full disclosure, it's not really my theorem. It's really the theorem of the author of the paper. And I acknowledge him in my paper. This was a theorem in his thesis. In his thesis, he only had to calculate the main term. In what I was doing, I needed the first order correction term. So I said, go through his thesis, and in this line, this line, this line, this line, this is what you need to do to isolate the first correction term. And so in my paper, I refer to his thesis. His thesis hadn't been published yet. So by the time he needs to publish it, well, I can refer to this. And so I was asked to review it. And so he could have written it up and done a little bit more general, but at the time, the main term was all that people cared about. And so to simplify the analysis, that's what he wrote about. You have to think when you're writing, and again, this is a class on math exposition, how much do you want to spend making your result as general as possible versus making it clear? So a lot of times, conference proceedings are terrific places to write up a special case in full, easily followable detail. And then you have another paper that nobody ever reads, where you go through and you put in all the technicalities and you do things in as great generality as possible. So this gives us several counterexamples to the monotone convergence theorem if we violate the assumption of non-decreasing. Okay. That convinces me that non-decreasing is important. Let's put back non-decreasing. And now we either have violate that it's non-negative or violate that we're using supremum. Let's violate supremum. Can you think of something to look at that's related to supremum but is not the same as supremum? Yeah, lim sup, right? Let's try lim sup instead. So consider fk non-negative, non-decreasing, show the lim sup of the integral of fk does not equal the integral of the lim sup of fk. So we want to try to find a counterexample. Where do you think we should go to look for counterexamples? Where might be good functions to look at? Right? We just came up with a bunch of functions here, right? These are now good candidates to try again. And maybe we'll be lucky and maybe one of them will work. So the more you know, the more likely you are to find a good example to look at. You want to start collecting things. You've done the ratio root test? Okay. So when you do the ratio root test, it's just pure algebra. You just grind through and calculate either the limit of the ratio or the limit of the root. There's really not much thinking that's required. Do you know how the ratio test and the root test work? What's going on in the background?
At one point I did. Geometry.
Yes. Looking in the background, there is a geometric series. It's a comparison test. And the whole point of what it's doing is it's trying to find what is the right geometric series to compare it to. The comparison test is a wonderful test, but it's a bit like art. What should I try? If I knew what to compare it to, then the comparison test is often very straightforward, but it's finding what's a good thing to compare it to. The ratio and the root test automatically find what geometric series to compare it to. And they hide a lot of those calculations from you. So over here, we're trying to come up with a good sequence of functions to look at. Well, one possibility is to try some of the functions from here. So knowing that, let's try again. Try to have the lim sup of the integral of fk. What should that equal? One or some constant. And so over here on the last page, one, all right, or a constant. Okay, I mean, if it's really a constant, I can always just rescale all the f's, so it's not that big of a deal. But we want the lim sup to have a large integral. We want the integral of lim sup of fk to be larger. So any thoughts about what would be a good function to look at?
What if it's non-decreasing, but the soup and the soup?
Okay, so now we have restored non-decreasing. So if we restore non-decreasing, what does that do to all the examples we had? They're all gone. So all previous examples are inaccessible. So now what's true about the limb soup and the soup? So the functions are non-decreasing. So now the same. So as the functions are non-decreasing, limb soup equals the soup. So we're going to find a counterexample. No, because in this case, the limb soup is not the same as the soup, but in this case they are. We could, of course, get rid of the non-decreasing and look at the limb soup of the integral versus the integral of the limb soup. But there's no point in doing that because we're now getting rid of two conditions. And we've already shown that if we just get rid of non-decreasing, we have a counterexample. So there's no reason to get rid of non-decreasing and simultaneously get rid of soup. So the only thing that's left is what happens if you get rid of non-negative. So I'll leave that as something for you to play with. But again, what matters to me is the thought process behind this. It's a wonderful result. And just trying to get a feel of why are these conditions necessary? We have some idea now of the kind of counterexamples that could arise if we get rid of non-decreasing. But it's called the monotone convergence theorem, not the monotone non-negative convergence theorem. How important is the non-negative? Is there a counterexample if you allow the functions to be negative? Do people want to try to find a counterexample? I'm happy to, again. All right, so let's try to find a counterexample. My wife sometimes is a little surprised about how math is sometimes taught. Well, what happens if you can't solve the problem? We think about it for next class. So assume the FK non-decreasing, but can be negative. Prove the supremum of the integral of Fk is not necessarily the integral of the supremum of Fk. Okay, I have a counterexample. What must be true about your function for the counterexample? What do you know about it? It must be negative somewhere, right? If it wasn't negative anywhere, then we would be back in the conditions of the theorem. So we know must be negative somewhere. And maybe we want all the integral of the Fk to be the same. What's different in how I wrote this and how I've written things before? So what's different? I didn't write equal to 1. So I can always adjust a common value to equal 1, except in 2 cases. What are the 2 cases I can't adjust?
It's negative.
If it's, no, I can adjust if it's negative.
But you would need a negative adjustment, right?
That's fine. If everything equals -5, I can just 0 and what else? Infinity. So this is a hint. Maybe 0 or infinity. And again, I don't particularly, I mean, I do like the monotone convergence theorem. I like the dominated convergence theorem. I am very proud that I have a paper in my collected works where I have to use the dominated convergence theorem. I feel like all of the advanced analysis classes I took were useful. But in most of my life as a professional mathematician, I don't use the DCT. I don't use these results. But the thought process I use. So again, I'm immediately thinking, maybe I want all the integrals to be 0, or maybe I want all the integrals to be 1. I still want them to be non-decreasing. So that kind of prevents me from doing some kind of like flip-flopping. So what do you want to try? Equals minus infinity or equals 0? Okay.
Like 1 and -1, and then have to switch over.
Okay, so let's try this. So trying integral of fk equals 0. And so what we're going to do is, here's 0. So you want the function to be 1 for a while, and then -1 for a while. And then what happens?
It's 1 for more and more time. Like eventually it'll be 1 by 4. That's the goal.
Okay. And then maybe this is k and this is minus k. So the integral will be 0. Yes? Is the function non-decreasing? Yeah. Or is it? Is this non-decreasing? So here is fk. You know, it's really easy to make these mistakes.
Left-hand side.
And here's, oops. And here's fk plus 1 of x. So it's not non-decreasing. So unfortunately, if you look at what's going on over here in these points, these were 0 for fk, and now they're -1. So this violates the, so it's not non-decreasing. So can we salvage this?
Just center it at K and have it go infinitely far in each direction.
So you center it at k,
But then there's still some portion where it's decreased from 0.
Oh, yeah.
right? And you're going to still have, you know, it's this non-decreasing bit. So all of our counterexamples in the first one was, we dropped the non-decreasing. Oh, it was really easy to come up with counterexamples. Now that we require things to be non-decreasing, it's a lot harder. This is really constraining us. And again, what you tried, it's the natural thing to do. I was thinking of, what if I did something like a cosine? So it might be possible to do it with the integral equals 0. Do we all agree we're having some trouble? What should you do if you have trouble? Try the other case, right? There's two cases. If you're stuck on case A, try case B. What happens if you're stuck on case B? Leave it till tomorrow, or try another case if you can, and if you can't, then maybe case A wasn't so bad. But we work on case A for a little bit. We're not making any progress. Let's see if maybe the other case is really simple. And if so, let's do that case. And if we're not having progress in that, crap, then let's look at the two cases and reassess. So now, let's trying the integral of fk equals minus infinity. So can you come up with a function whose integral is minus infinity? Simplest function you can think of. I always have to be careful as to what I'm allowed to say as a professor in the 21st century. I think you can think of a simpler function than -1 over x. -1, right? That's a much simpler function to think of. Right? One of the things I want you to get out of my classes is to be a smartass. This is a good thing. Go for the simplest thing you can try. So let's try f1 of x is -1. What should f2 of x be? Yeah, f2 of x is -1/2. What should f3 of x be? So, again, you have plenty of other classes at Williams that are going to give you a tremendous number of theorems. So at the end of the semester, you'll have this huge book of all the things you've proved. You're not going to get that out of 389. It's nice to have a class when we can just pause and really think about how do we do mathematics? How do we see connections? How do we generate these things? We were having, and again, I have to think enough so I have an idea of what I want to talk about, but I don't think about these counterexamples. I really try to put myself in as much of your shoes as possible. I don't know if there's any Doctor Who fans here. I was watching an episode of Doctor Who while jogging this morning, and they were in a situation where their only hope, because the doctor's mind was being read by an alien, is they couldn't let the alien get his knowledge, so he had to think of nothing. It's often very hard. As soon as you start doing some of these things, you want to think about it, you want to come up with, oh, let me play with this. So it's hard not to think about these things, but as soon as we had it was 0 or minus infinity, my first thought was exactly this: -1, -1/2, negative. It's either that or -1, and then maybe doing powers of 2, whatever, something like that. But this is really nice, clear, and simple. And now, what's the supremum going to be? So what's the supremum of fk? Yeah, so the supremum of fk of x is identically 0 for all x. And so the supremum of the integrals is not the integral of the supremum. Do you find this example unsatisfying? Yes. And again, this is a personal preference as to whether or not you find this unsatisfying. I find it unsatisfying. Why does this bother you?
Like, it's not only negative infinity, but also like different functions are, I almost want to say different sizes of.
So I mean, I guess what the way I would say I'm bothered is that the integrals are minus infinity. These are not integrable functions. But the integral of the supremum makes perfect sense. And so do I want to put in an additional condition that these functions have to be integrable? Well, one thing about integrable is if I put in absolute values, I have to get something that's finite. And so this will give me a plus infinity. So maybe I would allow it to, if I'm allowing negative values, it doesn't have to integrate to the absolute value of the integral doesn't have to be finite, but maybe I need the integral to be finite. And so I would say that I'm not fully satisfied with this answer. Is there a way to fix the integral of fk equals 0? Can we make that work somehow? If you take something like the Cauchy distribution, x over 1 plus x squared, that integrates to 0 if you integrate symmetrically, but not if you integrate in other ways. So I'll leave this as extra credit. Try to fix this. Can you come up with a counterexample? Now, we've already come up with a counterexample. Once you have a counterexample, it's done. But then somebody could say, oh, okay, well, I want to add another condition, which I thought was obvious, that the integrals have to be finite. Then our counterexample is no longer valid. And so in that situation, now we would have a problem. And so is there a way to fix things in that case? Notice that our functions in the case we have here are just strictly negative. So we don't have any kind of cancellation. So I'll leave that as extra credit to see, can you fix it? All right. How many of you have seen the dominated convergence theorem? Have you seen this one? All right. So this is one of the gems of measure theory. So imagine I have a sequence of functions that converges pointwise to f. And let's assume that there is some function g that dominates the f's. What does this mean? It means no matter what n you choose and no matter what x you choose, fn of x is at most g of x in absolute value. In that case, the limit of the integral is the integral of the limit. And in fact, an even stronger statement is true, that the limit of the integral of the difference in absolute value tends to 0. So this is the dominated convergence theorem. We have pointwise convergence, and we have some function that dominates. So the only way to violate this would be we can't have pointwise convergence, or we don't have some function that dominates. Notice that g does not show up in the conclusion. So this is g independent. Are you surprised that this result is g independent? Should the limit of the integral of fn depend on the function that's dominating it? No. Is the function that dominates it unique? What could I do to g and still have it dominate? Times 2. I was actually thinking times 4. I don't know why I was doing 4. Times 2 is better. I could multiply by any positive constant. I could also add on any non-negative function which integrates to a finite number. So g is not unique. Reasonable. G is not unique. I could do g of x goes to a squared g of x plus b of x greater than or equals 0 has finite integral. So anything along those lines would work. And there's other things I can do, but this is enough to show you we have lots of different things. And depending on whether or not I'm working on a finite interval or an infinite interval, that impacts what choices I have for b of x. So it shouldn't surprise us that the result is independent of g, but we need a g to exist in order for the conclusion to hold. So what I want is sequence of functions fk such that the limit of fk of x equals f of x, but the limit of the integral of fk does not equal the integral of the limit of fk. Does this make sense? So again, I want a situation where I can't interchange orders. So we have to somehow violate the condition that there's a dominating function, which is integrable. So the whole point of the dominating convergence theorem is there's some function g, which is pointwise larger than the absolute value of fk everywhere, and the integral of g is finite. And that's going to then force the integral of f. The limit of the integrals of the fk's to be the integral of the limit of the fk's. So what do you want to have for the value of the limit of the integral of fk? What do you want to assume about that? What would you like each of those integrals to equal? Constant. And what constant? Yeah, so now we're back to trying to make that the constant 1. So I want to come up with a sequence of functions that integrate to 1, and that converge pointwise, but the limit of the integral is not the integral of the limit. We've actually seen an example earlier in the semester, I believe.
With the box, like there.
Yes, and what happens to the center? Where's the center going to? Okay, so that's one way to do it.
Is that nicely measurable though? Wasn't that like a condition?
Yes,
for-
and it will be nicely measurable. And again, I'm glossing over what measurable is because real analysis was a prereq for this course. Measure theory was not. So imagine we have our interval here, and here is n, and we could do maybe n plus 1 over 2n. I'm sorry. N plus 1 over n maybe, and then n minus 1 over n, and height n over here. And so now what's the area under the curve? 1. And so now the integral of fk, well, I guess this is fn, of x dx equals 1. What is the limit as n goes to infinity of fn of x? For any x, 0. So the integral of the limit of fk is 0. Do we need to go up to height n? So we have a function that's getting very large. Maybe if our function was bounded, this wouldn't be a problem. Can you remove the fact that it's exploding?
Make them all the same height.
Yeah, make them all the same height. So doesn't have to go to height n. So we could just do n, and then over here, n plus 1, n minus 1, and just a height 1. And that would also work as well. And so now we're able to have the functions bounded, but we do have an unbounded interval. So can you do this with a bounded interval? What are your thoughts?
It's basically the same example we gave for the one.
So which example? Okay, so yes, we could do triangles with area 1 centered at, say, n alpha mod 1, where we do wrapping. And what's nice about that is it's going to be, each function is going to be bounded, and it'll be on a bounded interval. But there is a challenge here, there's a difficulty. What's bad about this? So there's an issue with your example. So let's go back.
Oh, need to
Yeah. The limit of Fn of x does not exist. So we wanted to have, point-wise limit exists. This doesn't work. We could try to do so that was the first failure. We could try to do, oops. It's so our second one is could try maybe Fn mod 10 of x, but the limit of Fn does not exist as well. So the problem is keeping things bounded is causing issues. We're losing convergence. So what we need to do is we need to have our function converging, which means more and more of the mass has to be over small and smaller intervals. And where it's concentrated has to be moving. And once, again, this is a liberal arts college, so you're supposed to be well-versed. I think it was Omar Khayyam, the moving hand having wit moves on, and neither all thy strength nor wit can get it to remove one bit, something like that. Once we've had the action at a point, it's got to move so that it never comes back there. So it's once it becomes 0, it stays 0. If we keep things bounded, it's going to be forcing it to cycle around. So what's going to have to happen to the function? At some point, it's going to have to be going to what? It's going to be going to infinity. And so this is one of my favorite counterexamples. Here's 0, here's 1, here is 2 over n, 1 over n, 3 over n, and then have the function go up to height n. And because I have that long stretch in the beginning, it's always going to be 0 at 0. And as n gets larger and larger and larger, this bump is getting bigger and bigger and bigger and bigger over small and smaller and smaller intervals, converging towards the origin. And thus, eventually, you give me any x, I choose n so large that 3 over n is less than x, and thus Fn of x is going to be 0 for all very large x. So now we know that the limit of Fn of x is identically 0. We know the integral of fn of x is always going to be 1, and the integral of the limit of fn of x dx is going to be 0. And so the problem is we don't have one function that dominates it. Each function is integrable, everything's non-negative, that's not a problem. We're on a bounded interval, that's not a problem. The challenge is without that function that constrains it, it's able to spike up. And it's spiking up over shorter and shorter periods. So this is a class on order of operations. When can we switch things? We can't always switch things. Here is an example where things fail miserably. And it shows you why we need these conditions. It doesn't show you that these conditions are sufficient. There could still be counterexamples. Probably not, because they have a Wikipedia page. And your Wikipedia is pretty stable in mathematics. In politics, it often depends on which side was the last side to edit. But in mathematics, we don't really have that many disputes over basic concepts like this. I'm not going to do Fatou's lemma. I'm going to just state this is the third of the big 3 analysis results. This was the promised part of my algebra oral exam at Princeton. So Katz asked me to write down the definition of a group. This was the start of the group theory section. I commented, and this is where it's always dangerous to show off or be a little. And so I just remarked that it's sufficient to have just a left inverse and a left identity. So then I was immediately asked if it was enough to have a left identity right inverse. And I had read a lot of books, which is why I made the remark that it's enough to just have a left inverse and a left identity. And so using the advice from Peter Jones, I go, well, I haven't seen this in Hungerford, I haven't seen this in Jacobson, I haven't seen this in, and I just went through quickly in my mind all the books I read and not one of them. So I said, that's not enough. And he says, good, now prove it. And so I think I came up with, I can't remember if it was playing with sets of 2 or 3 elements, I came up with a counterexample. So I'll leave that for you if you've seen group theory to just come up with a counterexample where you have a left identity, but only right inverses. So you don't necessarily have a right identity. And in fact, you don't have a right identity. For the next class, I might talk about the other part of my oral exam where I was a smartass on an integration problem and just how they rolled with it. It's an interesting experience taking an oral exam. Oral exam is very different than a written exam. The problems on written exams are much harder because they can give you problems where you can just need 30 minutes to an hour to think about how to attack it. They'll be bored if this is an oral exam. But one of the things that's nice is they can make the oral exam dynamic and they can adjust it based on what you say and what you do. So if people are enjoying stuff like this, the next class I'll talk about the other one, which was a complex analysis question. Talk a little bit about Fubini-san, which I think we've done. And then here are some fun ones to think about. If the sum of non-negative terms is finite, must the terms tend to 0? If the integral of a non-negative function is finite, must f of x tend to 0? And then similarly, if the sum of a non-negative terms is finite, must the sum of the kth powers be finite? If the integral of a non-negative function is finite, must the integral of its kth power be finite? And then the last one is the fundamental theorem of calculus. How many of you have seen a proof of this? How many of you could prove this if you had to? So when I used to give blood, I would check to see if I was able to leave by could I quickly go through the proof of the fundamental theorem of calculus. I remember one time after giving blood at Brown, it took me too long in my mind to prove the fundamental theorem of calculus. And I decided I need to wait a little bit longer before I can leave. And so the question is always, what do you want to assume? So this is, let f be a continuous real valued function. When I prove it, I often assume f is a continuous real valued function, which is differentiable, and f and its derivative are bounded on the interval. That's a lot more to assume. And so the question is it necessary to assume all that? No, because I got this from Wikipedia. And so clearly this is fine. But maybe the proof is a lot harder if we don't assume that the function is differentiable. And so here, you probably have noticed immediately the words uniformly continuous. And so if I assume that my function is differentiable with bounded derivative, I don't have to worry about uniform continuity, and I can use a lot less analysis. And that's what I mean by, if you often put in additional constraints, it makes the proof easier, but then it's no longer as applicable. All right, so this is a good place to stop. Just hit